Not all sinusoidal waves start at equilibrium or an endpoint. Some waves are shifted on the x-axis. In fact, even a cosine wave can be considered a shifted sine wave. And we can see the shift term right here in the general equation. So the general form of a position function that includes a shift looks like this. So you can see it's the general form that we've had before, and then we just add on that shift. In this example, the shift is the Greek letter phi. And in different websites, different textbooks, maybe even different courses, sometimes they use different Greek variables, and sometimes they give it a different name. Sometimes it's called the phase shift, the phase constant, or the phase angle. I'm going to always use the term shift just to indicate that it's shifted on the x-axis. The last thing I want to point out is notice that we're taking the product of angular frequency times time. We're adding on the shift, and then this entire quantity is what we're taking the sine or cosine of. What we really need to be able to do is to extract information from a function. So here's an example. The function x equals 0.2 cosine of the quantity 1.25 pi t plus pi over 5 describes the simple harmonic motion of a 3 kilogram oscillating mass. Just looking at the function, we know it's a shifted wave because of this term right here, the pi over 5. So that means that if we graphed this function, it's not going to start at an endpoint or at equilibrium, but the wave's going to be shifted over on the x-axis, pi over 5. So let's see what else we can extract from this position function. Letter A says, what is the angular frequency of the motion? So we have to know that in this big function here, that this term, 1.25 pi, is the angular frequency term. So we can just write that down. Angular frequency is 1.25 pi. I could multiply it out and get 3.93 hertz, but that introduces a little bit of round off error. So part B says, what is the frequency of motion? We know that angular frequency equals 2 pi f, so I'm going to use the 1.25 pi version for angular frequency equals 2 pi f, and now you can see that the pi's are going to cancel, and I'll get a frequency of 0.625 hertz. And letter C says determine the period of the wave, which is 1 over frequency, and the period is 1.6 seconds. Letter D says, what is the displacement of the mass at a time of 2 seconds? So we can now use our given position function to calculate the position at a time of 2 seconds. So let's talk through that. So we have the angular frequency of 1.25 times pi, but now we're going to plug in a value for time, which is 2 seconds, and we still have our shift that is hanging here. So we have to do the algebra of this entire inside quantity, 1.25 pi times 2 plus pi over 5, and I got 8.48 when I did that. So now I'm taking the cosine of 8.48, but remember my calculator is in radians, times 0.02, and I get a displacement of negative 0.18 meters from equilibrium. Letter E says, what is the velocity of the mass at a time of 2 seconds? So we're going to get the velocity function by taking the derivative of the position function. So just a reminder that the derivative of cosine of x is negative sine of x. So my cosine became a negative sine. And then I also have to take the derivative of omega t, which is omega. So I pull that omega out, and that's how that ended up here. Notice that I'm not really doing anything with the phase term other than keeping it as I move from position to velocity to acceleration. So now I'm ready to plug in my numbers. So we know that the angular frequency is 1.25 pi, so I plugged that in there. I'm going to plug it in here, 1.25 pi, and we are trying to find the velocity at a time of 2 seconds. So doing all of this algebra here, I got my 8.48. I took the sine of that in radians is 0.81. Multiplying all that out, I get a velocity of negative 0.64 meters per second. And letter F says, what is the acceleration of the mass at a time of 2 seconds? So again, we're going to get the acceleration function by taking the derivative of the velocity function. So the velocity function has a sign in it, and the derivative of sine is cosine. So the sine became a cosine. There was a negative out front, so obviously that is staying. But then I also have to take the derivative of omega t, which is omega 1.25 pi. And so that became a 1.25 pi squared. So again, plugging in my 2 seconds here and doing this inside term is 8.48. Taking the cosine of that is 0.59. Multiplied by everything else in the equation, I get an acceleration of negative 1.81 meters per second squared.